Okay, dear students, last time in the last lecture there was some problem with my, there still is some problem with the marker, this pen. Okay, and we talked about direction coefficients. Essentially, we said that at every point on a surface there is a triplet of vectors which are linearly independent. One was our R sub u and R sub v, which span our tangent plane. So this is our tangent plane on the surface, and then there is the unit normal which is perpendicular to both of these, which means that n, of course, r sub u, r sub v, they are three mutually perpendicular vectors, and remember that this is basically a tangent plane on the surface at this point. We just imagine ourselves, so I'm not drawing it that well. So now at each point in this, any vector here, somewhere here on this point, say let's call it a, I have also written a little here, can be written as a linear combination of these three vectors, and we denote it by t, the tangential component of that vector, that is lambda times ru plus mu times rv. Then we took the unit vector e along the direction of t, that means this vector, and we denoted it by, of course we denoted it by, we called its components L and M, so it was L times Ru plus M times Rv. And these two numbers Lm, because as I told you last time, since I know what the basis is of the tangent plane, I denoted this E by Lm and call this pair of numbers direction coefficients at this point on the surface in this direction. So in a different direction on the surface, I would have another pair of numbers, which you can denote by another numbers. So that is the definition of the direction coefficients, which is given in the notes. So you can actually read it from there and write it from there. Now suppose I have got two different directions at a point given by two different. I've got one direction here, another direction there. And I want to find the angle at this point, angle on the surface between these two directions. What I do, I take their differential coefficients. And suppose the direction coefficients of one direction are Lm and another direction are L prime M prime. And we know how to find, it should not be difficult to find. Now this is my vector E, let's call it E, and this is the vector E prime. These are unit vector along the tangential components. When I write these two vectors in terms of the local bases R sub u, R sub v and n, when I write these vectors in terms of these three vectors, then these are its tangential components. Then if omega is the angle between two directions, omega is the angle between these two directions, then I know that cos of omega is E dotted with E prime divided by norm of E into norm of E prime. And norm of E and norm of E prime is equal to 1. That means it is just E dotted with E prime, and if I write the components of E and E prime, so that it is basically L times E R sub u plus M times R sub v dot product L prime times R sub u plus M prime times R sub v. And if you expand the product and use the fact that Ru dot Ru is equal to E, Ru dot Rv is equal to F, and Rv dot Rv is equal to G, then this is nothing but E L prime plus twice F, not really twice, it should be basically, because I have a different number here, it should be इसको डिलीट करते हैं हम. It is basically, I write here, plus f times lm prime. It is just evaluation, so no problem, you can just evaluate it yourself, plus g times mm prime. So that would be the cos of omega, and if I want to evaluate sine of omega, so sine of omega is nothing but sine of omega would be cross product of e vector with e prime, I mean e prime vector इसकी length divided by of course norm of e into norm of e prime, which are 1. So that would give me, you can easily evaluate them by taking the cross product of the two vectors. It would be L m prime minus ml prime whole divided by, no, not whole divided by, because division में तो 1 है, multiplied by h, where h is equal to ru cross rv, the length of this vector. So again, tan theta is sine theta by cos theta. So we call now these are our direction coefficients lm, and by the way, the original numbers, lambda and mu, are called direction ratios. Now these are direction coefficients and direction ratios. It is the same as, if you know those, what you have done in your 11th 12th classes, what we call direction cosines and direction ratios of a line. Direction ratios are basically the components of any vector in the direction of the line, but direction coefficients is a specific thing, it's a vector of length 1 in that direction. Similarly, direction coefficients here are the vector of length 1 in the direction, in a direction at a point on a surface, whereas lambda and mu is any vector in that direction on the surface. So if you divide lambda mu by the magnitude of the vectors, we will get direction coefficients, the same as in your earlier classes. So there's my direction coefficients. Of course, they are proportional. Now, in case these directions are perpendicular, if their directions are perpendicular, then of course cos of omega should be 0. In case these two directions on a surface at a point, suppose they are perpendicular to each other. So this has direction ratio, say Lm, and this has direction ratios L prime M prime. We already know then cos of omega, if omega is the angle between them, then cos of omega should be 0. But if we look at the formula above, cos of omega is equal to this thing, E L prime plus F times Lm prime plus L prime M into G M prime. So if that is 0, we should get something, a relation in terms of the direction ratios and the first order fundamental magnitudes. So that means I should have in that case E times L prime plus F times plus F times plus F times L M prime plus L prime M plus G times M prime should be equal to 0. Now this would be the condition under which the two directions on a surface are perpendicular, and if I write it in terms of the direction ratios in that directions, then I would have a similar thing, because it would be just have to do divided by the magnitude. So it should be just E lambda prime in terms of direction ratios. The relation would be lambda mu prime plus mu lambda prime plus G mu into mu prime equal to 0. And remember, I've got two directions, and one direction has direction ratios lambda mu, and another one has direction ratios lambda prime mu prime. And if those two directions are mutually perpendicular, then this should be the relation. Okay.